Okay students, welcome back to the next question, Physics Pathfinder, 6th question, Challenger problem in rotational mechanics. So let's get into it. This is also an interesting question. It has got two parts to it. First question, first part, let's see. Light ring, meaning massless ring of radius r, wearing two identical beads. Ring is wearing, it seems, as if you are wearing rings like that. Okay, it is wearing two beads A and B, each of mass m, and is hinged at top point O. So O is the hinge point there. So about that hinge it can rotate like this. The ring can rotate about the hinge, like a photo frame can rotate like that. Okay, in such a way that it can rotate freely in its plane about a horizontal axis through hinge at O. Okay, right. The bead A is affixed, it is attached, welded on the ring, and the B is held so that they occupy positions of the ends of the horizontal diameter of the ring. So that means B is not affixed, it is just kept there, it can pass through. It is beaded, bead is beaded. Okay, but right now it is occupying a horizontal diametrical position. Alright, very good. Right now the system is motionless, the ring is well lubricated so that friction can be neglected. Determine acceleration of the beads immediately after the bead is released. The moment you release it, everything was stationary and then you release, then what would be the acceleration of B? So that is one thing. Only acceleration is asking, no, both the acceleration is asking. That is the first part. The second part would be find angle of rotation of the ring when all motion ceases after a long time due to the little viscous friction between the bead and the ring. Okay, so as B is oscillating and ring is oscillating, complicated motion, finally oscillate, 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 and finally it comes to rest. When it comes to rest, what would be the angular orientation of the ring he is asking about. So these two parts we have. Right, first let's focus on the first part where we need to find the accelerations. So whenever you are asked to find acceleration, alright, there are certain methods to find, it is very straightforward. First method would be method of kinematics, that is what you study in physics first, kinematics. So there the position of the particle is given as a function of time, velocity of the particle is given as a function of time, our path is given, x is given as a function of time, y is given as a function of time. So you have variables x, y or by, bx, by, so that you can simply differentiate and find acceleration. That is called method of kinematics. So differentiation method. Method of differentiation is what you have it. Okay. Then the next method is, now position is not known to you, the path related information is not known to you, but external forces are given. So when you have external forces, you can apply Newton's law of translation and also of rotation to find the accelerations. So that is called method of dynamics. So you can find acceleration either from forces or from the position and velocities. Sometimes even though you have these two, sometimes the unknowns may be more than the number of equations you got, then we will also use method of constraints. The question sometimes would be so easy that only by constraints you can get it, but sometimes you may have to add this constraint idea as a supplement to get additional equations. So this is a general procedure, but when you go for some really good questions, some higher level questions, the method would not be so clear. So you might have to use a hybrid method here. A little bit of kinematic idea you have to use, little bit of dynamics you have to use constraints also depending on the situation. Let's say for example they gave the path, but they didn't give the x and y as a function of time or bx and by as a function of time. They just mentioned that the path is parabola or a circle, something. So partial information is given about path but not complete. So completely only using kinematics method you cannot solve it. And they have given some external forces but not all external forces. Some of the external forces are unknown. Then that is also a problem. You can't completely depend on dynamics method only. And of course constraint equation is always there. So there is this hybrid method where you will have to use both, in fact all the three. You will use kinematic equations, you will use dynamic equations, you will use constraint equation also. So in this particular problem we have to look at it that way. So that is a basic idea. Now let us get into finding the acceleration. First motion of A let us focus on. So I am taking motion of A first because that is easy to analyze, because it is welded to the ring, right. So the ring is rotating, along with that the bead A also will rotate. So what would be the motion of the particle A? It will be circular path. Need not be a full circle, but circular path. As long as it goes in a circular path of radius root 2r. That is the distance you have. R down and R horizontally, root over r square plus r square. Root 2r is the radius in which it will oscillate. Alright. So that is circular path you have. And released, so initial angular velocity is 0. So whenever a particle is in circular motion, kinematics suggests that it will have two kinds of acceleration. One is centripetal acceleration and the other one is tangential acceleration. So kinematic method I am approaching here. Using kinematics of circular motion, I know that it should have centripetal acceleration omega square into root 2r and tangential acceleration is r alpha. But the point here is omega initially 0, he is asking just after release, no? So that time omega 0, meaning it has no centripetal acceleration. It has got only tangential acceleration. The tangential acceleration will be perpendicular to radius. That is what you have, perpendicular to radius you have it. So much about the motion of A, and A equal to radius into alpha, where radius is root 2r there, and you see it is perpendicular to radius there. Okay. So motion of A, we could use a little bit of kinematics, not completely, because alpha is not known to us. We could not solve it by completely only kinematic method, but definitely it has given some insight about the motion of A when you go through the kinematics of circular motion. So that is about motion of A. Now let us go to B here. B motion is a bit complicated because B is not welded to A, the ring there. It can go in x direction anyway, it can go in y direction anyway. Of course, it has to be on the bead somewhere, need not be at the same point on the bead. It can be slide with respect to the bead, that ring there. So the motion of B is a bit complicated. So you can't go with the kinematic equation straight away. So I will discard the kinematic method for understanding motion of B. I would rather go with the constraint equations, because it is inside the bead, right, inside the ring there. So there is a contact between the ring and the bead, and so I can use that wedge constraint or the surface contact method. So what does it say? Along the normal meaning radial is basically horizontal here. Both the particles should have same acceleration. Along the normal, both the particles should have same acceleration. So that is one thing that I have here. Okay, so that means AX has to be equal to ABX, and that is going to be R alpha. So I have just put one step ahead, because actually you are supposed to focus on here. This point will have acceleration in this direction, resolving it R alpha there. So anyway, A and this point will have the same acceleration, that is alright. AX equal to ABX is equal to R alpha. So we got another equation. So constraint equation helped us to understand the motion of B, but still only one equation we got. Look at unknowns here. AX is not known, ABX is not known, AY is not known, ABY is not known, alpha. So there are 5 unknowns, but we only got 2 equations here. So not very comfortable, probably require 4 unknowns, 4 equations. So 2 we got it. So we require 2 more equations here. So number of equations anyway now less there. Okay, let us go on with the other method. I will use dynamics also, apply Newton's law also, alright. Newton's law of translation and Newton's law of rotation, both I will try to use now. See, we have used a bit of kinematics, we have used constraint equation, now we are going for method of dynamics here. So particle B, if I consider, because particle B is free to move, forces are easy to handle there, only normal reaction is there, friction anyway they neglected it. Normal reaction will be normal to the ring, that is it passes through center, meaning it has to be horizontal. So only for B I have drawn the free body diagram here, only for B I have drawn the free body diagram, alright. So you see there are only 2 forces acting, mg vertical and n there horizontal. So horizontal force produces horizontal acceleration, which ABX is nothing but R alpha, vertical force produces a vertical acceleration. So we got ABY equal to G, okay, and N equal to M into R alpha. I got one equation, but we got one unknown also extra there, not very useful. Okay, now let us look at particle A. In particle A situation, I do not want to use Newton's laws of motion, translation Newton's law, because if I have to write translation Newton's law, I need to find the force between A and the ring, and that is complicated because it is welded. No? It will have normal force also, it will have tangential force also. I do not want to open it, right. So let A be attached to the ring. I am going to take the entire system like a ring and bead A, and then try to write the free body diagram. You have mg there, internal force. So force between bead and ring I am not considering that, let it be internal. So total system mg is here, normal reaction from the bead B, you see on bead it is in this direction, meaning because of bead it will be in opposite direction, okay. Then the hinge force Fx and Fy you have it. So that is there, okay. Anyway, torque due to Fx and Fy will be 0 because they are passing through O, that is understood, these two will become 0. Torque due to mg into perpendicular distance, mg into perpendicular distance will be r only. So that way mgr you have, but it is trying to rotate in this direction. Normal reaction is like this and it is perpendicular distance is this, so that is also going to be r. So the net torque we got mg minus n into r, and that should be equal to I about O into alpha. Here ring is anyway massless, only particle A we need to focus on, and particle A is at a distance root 2r from O. If you substitute there, you will get G equal to 3r alpha, otherwise alpha equal to G by 3r. Very good. Now we got the sufficient equation. You see what are all the things we used kinematics for A, we used a constraint equation for B, and we also used dynamics for translation, we also used dynamics of rotation. Everything has to be used here to solve them. Okay, once I have alpha, ABX is equal to R alpha, AX equal to the same thing R alpha, you got G by 3, and AB equal to root over ABX square plus ABY square, and we got it. So AA and AB we got it. So simplification we got it. So I hope you understood the method basically. Simplification you can look at it. So that's the first part. Right. First part is over, sir. Now we are going for the next part. What is the next part? They are talking about the angle after a long time. So after a long time, oscillator, you just wait for it, you sleep for some time, you come back once it comes to rest, then we will focus on it. Now let's focus on bead B because it is anyway not attached to the ring. So forget about it. So B, if you consider, there are only two forces acting on it. One is mg, vertically downward. The other one is contact force between bead and the ring. And we have seen friction is neglected, only normal reaction. So only two forces will be there, and at equilibrium, finally after a long time it will come to equilibrium, na? So mg and normal reaction put together should balance each other. That means n has to be minus of mg. What is the meaning of mg down? Mg is down, okay, but normal reaction has to be vertically upwards. So from this analysis I must say that n bar must be directed vertically upwards. This is one logic. Finally after a long time when the body comes to rest, mg and n has to oppose each other. Mg vertically down meaning n has to be vertically upwards. That is logic 1. Okay. Logic 2. Normal is always normal. What does it mean? Normal is always perpendicular to tangent. Normal always passes through center of the curvature there. So normal must pass through center of curvature is another logic, that's absolutely okay, always true. And so combining both of them, normal has to be vertical, normal has to pass through center, meaning center has to be vertically above bead B. They have to be on a single vertical line. Using logic 1 and 2, I see that B has to be right below center of curvature. So that is one logic. So where is B? B has to be right below the center of curvature finally, otherwise normal reaction will not be vertical. So that's one point we have it, right. About B we have got it. Now let's go about A. I think I have taken another slide for it. A, where should A be? A is attached to the ring, it can be anywhere, need not go to down only. It has got a complicated contact force between ring and the bead A. So we cannot just focus only on horizontal force or vertical force or normal force there. So what I would do is, I look at the rotational equilibrium of A and entire system. Let's look at the entire system rotational equilibrium. See, I am looking at rotational motion for bead A, because if I open A, right, there will be some unnecessary extra unknown forces. That's why I am holding it together as ring and bead A together. So I am using rotational equilibrium here. Torque about hinge I want to use, sir. So torque about hinge will be hinge force anyway, torque will be 0. Then what are the other forces you have it? You have mg, that's all. Entire system if I consider. What about normal reaction between bead and the ring? Bead B and the ring, that will be internal force if I take the entire as a system there. Okay. then what is that you have torque about hinge has to be 0, meaning mg of A should balance torque of mg of B. So that means the perpendicular distance must be equal, alright, perpendicular distance must be equal. Once I had that, now we will go for geometry here. So bead B is already, we have decided that it has to be right below center of curvature. Bead A has to be somewhere on the ring in such a way that you draw a vertical line from O, and that vertical line should be equidistant from both A as well as B. RA must be equal to RB, only then the torques will be equal there. So that is one point we have got it. After that you look at geometry there. See, you join bead O and A and O, that is root 2R, no? Root 2R we have already seen, right? A and O, they are root 2R distance there, okay. And O to C, that is R, this is root 2R and this is R there, very good. Now I drop a perpendicular, EC you will get AD. I am creating two triangles, right angle triangle. See, in physics geometry meaning right angle triangle only mostly. I created two right angle triangles, sir. One right angle triangle, what is that? OAD, the other one is OCE. In both you have the horizontal sides, AD and EC, they are equal. So I have to equate them to find that. And one more thing is this angle is alpha plus beta 45 degrees, because this is isosceles, no? This is R, this is R. Isosceles right angle triangle meaning the angle has to be 45 degrees. Very good. Okay. Right. AD you will calculate from the bigger triangle, that is AO sin alpha, and EC I will calculate from the smaller triangle, and that is CO sin 45 minus alpha. Equating that I will get alpha as equal to cot inverse of 3 there. So this is a geometry part also I have completed. So with that the problem is solved completely, and it is a very classical good question properly within IITJEE advanced syllabus. Probably entire thing will not be asked in one question, but concepts are very relevant. I hope that you understand well and you have the strategy also followed there. So with that I will conclude here. Goodbye.